details that I get kind of from sometimes, but yeah, overall I thought it was okay for sure.
Hello, Matt.
Hello.
Well, thanks. So I decided to be in this room today. We'll see how it goes. Do you guys see any difference? Probably not.
I missed this room.
Oh, you missed this room. Yeah.
I like the way it looks in there.
You said I like what?
I like the way it looks in there. I like the board.
Oh, you like okay.
It's a lot closer, easier to see, and
So Borden and Christian, you are the only one who come to the class. So let's officially we're supposed to be there, but we're going to be here. Unless someone in between comes and says that this room is reserved for someone else. So unless that happens. Okay, I think 1, 2, 1, 2, 3, 4, 5. How was the exam? Any comments, Borden? Reasonable? Yeah. Questions are reasonable.
I didn't think it was too bad.
Yes, Matt? Matt, repeat that.
Yeah,
I think
the test was pretty. Oh, my internet's probably crappy. I didn't think the test was too bad.
Okay, good. Jeremy?
It's all right. I still just suck at finding the current density. I don't know why. It's just I had to work yesterday too, and that was when I had the time to do the test. So I was kind of tired, but like I've been struggling to do current density for a while. I mean, it's been kind of a long time for me anyway, but
Okay. Maybe I'll today we will be writing a current density for something. So at that time, maybe I'll try to go slowly and see if we can do something. Yeah.
that sounds good.
Yeah. Curtis, you did fine.
Yeah, the test was fine for me.
Okay, good. Thanks. Okay. Homework 4 I haven't posted yet, but I'll make it due. Probably will post it today in a few hours, and it will be due on next Monday. Midterm 2 is a little bit far. Now that's okay. So we talked about working out the magnetic field for a circular wire in an approximate way. Circular wire, and so the diagram will look like this. So that's your the axis, that's the current I that is going through, and let us say we have a radius A for this loop of wire. The first thing we should ask is what is the current density for this wire, and what I have been suggesting is that first note is that there should be a dimension of 1 over area. That's one way to look at it, but if not anything, look for where the wire is. The wire is probably the z plane. If I choose this to be the z axis, right, that's in the z plane. I can say it is z minus z naught, right? Z minus whatever is the position of this plane. Is that clear? So that's your x, z, and y will be coming into the page, right? So y has to be going into the page. So the so the loop of wire is in a plane, so that's z equal to z naught, and the wire also fixes the radius, right? So it is a rectangle, cylindrical coordinate rho that fixes that. So that's rho minus a, where rho is equal to, so remember your rho is x squared plus y squared, polar coordinate. So if I fix these two, I should get my current density, or that should be your area. That's one way to look at it. But we don't know what is there in front of this. So say that's constant C. So that's usually the confusion as to how do I get that C in there. Does that help, Jeremy?
Yeah, the C was like the struggle. I think I understand the right side pretty well.
Okay, great. So if you know these two, then typically what I suggest is that keep it as C. Don't worry about how to get the C. And here is how you will get the C. Okay. Now the current when it is going through an area should be I. So first pick an area. So this is the way you will normalize. So the current passing through an area has to be equal to I. So this is not a closed area, right? So this is just a. So think of that is a wire, and now you want to capture it inside an area. So this is your area, and I can choose. So that's my. Is that clear? So that's your current I. We know that there is a current going through this wire. If I cross it with an area and calculate the current density all over that area, I know that there should be a current I that is passing through. That's a physical constraint if you want. So pick an area of your choice, but typically since you want to do an integral, you will choose it of a convenient area. And in this case, we will choose it to be the XZ plane. So what is happening here? So this is X and this is Z. And the circular wire goes into the loop this way and comes out from here. Is that clear?
You scoot it down a little bit.
Oops.
Thank you.
Yeah. So what I was saying that if there is a XZ plane, my loop of wire looks like this. It is going into the page at distance A, and it's coming out of the board at distance A from here. Is that clear?
Yeah.
So let me pick my area to be somewhere here. That could be my area. And I'm sure that the loop of wire is going through that area once. To make this convenient, I'll increase this area to all the way to the half plane of XZ. So area would be equal to half plane of XZ. Reasonable? Then do the integral. What is the area for that? So what is the perpendicular vector? Either I can pick it outside or inside. Since the current is going inside, I'll pick it to the inside. So that's in the direction of y, right? So it is y hat. So this is dA times y hat dotted with j. So that's that has to be equal to I. area on a half plane. This is, we are doing rectangular coordinates, so I can do d rho, rho, d rho, or actually, careful, we have to do x and z, right? So hold on. How do I do this? So this is dz in one direction, and dx, but I'm doing what? Help here. What is, so this is dx, I suppose, right? So this is dz times dx, going from minus infinity to plus infinity, minus infinity to plus infinity, and I have y hat times j hat. So I should actually go back and fix something, right? There was a small error, small or big error, I would say. If you go back, the c should be a vector, right? Left hand side is a vector, so c should be a vector. So c is a vector there. So this is c vector c, and you have delta of z minus z naught times delta of rho minus a times this is equal to I. Okay. Does this work? How does this work? Up. Yeah. So actually just do it, I suppose, right? So C can have dependence in let's say Z, like let me say that C can have dependence in Z, comma, rho, comma, phi. That's the dependence it can have. And we just fix it using this. So this is when I do this integral, I get y hat dotted with C evaluated at C equal to Z naught and rho equal to A, right? That's what it actually does, this integral, and that's equal to I. That's all we have. And what will C be? First of all, we know that the magnitude of C in the direction of y hat has to be equal to I. What is the most general C you can write? This could be C in the rho direction, rho hat, plus C in the phi direction, plus C in the z direction. So probably what I should have done is that when I'm writing C itself, I should have picked the direction. I know the current direction to be in the tangential direction. So I should have picked that here. So if I had chosen that right away there, so this would have been what would have contributed. So this does not contribute. This does not contribute because of the physical nature of the wire. And what we then have is y hat dotted with phi hat times C of phi is equal to I. In the plane we are talking about, y hat dotted with phi hat is exactly equal to 1. And we get C phi is equal to I. Did I help this, or this was too confusing? Probably it was too complicated. Jeremy, did that help at all?
I think I understand.
Okay, so again, maybe what I should have done is, when I said C there, right, I should have picked the direction of C right away, because I know that it is in the tangential direction. That's your I. It is in the tangential direction. So I should have, like, it would have been simpler if I had started with this C times phi hat times rho of Z minus Z naught times rho minus A. Like put one more constraint right away. Is that, does that, is that step okay?
Yeah, I mean, I think it makes sense with just the regular vector for me too, though, because I mean, the phi hat direction is the y hat direction.
That's correct.
Yeah.
So my point is that, okay, maybe I didn't pick a good example, but if you choose at C and then use your normalization using this to get your constancy. So for now, let me proceed and yeah, I thought I will clarify with a better example. Let me proceed and ask me again, okay? Ready? Okay. Any other, well, did I confuse anyone else? Probably we are done examples right before. Okay, so if I go back and impose this, okay, so this says that this is actually I, or direction is phi hat, and I. It's also at this stage good to check your dimensions. Current density has to be current per unit area, and each delta function usually has that inverse dimension of the argument. So here it is length, so it is delta function is 1 over length, so that's the area. And phi hat is cosine. Remember, your phi hat will be cosine phi in the I hat direction plus sine phi. Oops, what is wrong here? What is wrong in that? Or what is that equal to? Oh. Notice that if you have a circle in your polar coordinates, so that's your unit vector, or the radius vector if you want. That's vector r, and that's your angle phi. So that's vector r hat if you want. If I divide this out by the radius of the vector, that's cosine phi. And phi hat is tangent to this, which if I were to move this across, that's around there. If that's angle phi, that's angle phi. That's your phi hat, that's your phi hat. That's the same vector, I can move it parallel to each other. So since it is in the second quadrant, its x component is negative, and since the y is adjacent to the angle phi, so that gets your cosine phi, and that's your pickup. And they are perpendicular to each other. If you notice the dot product between these two is equal to 0, right? Like cosine phi minus sine phi plus sine phi, so it's perpendicular. So that's something useful you should keep in mind all through. Okay, with all that, that's the first step. We want to calculate the magnetic vector potential at some arbitrary point r. So that's your magnetic vector potential at an observation point r. And it gets contributions from all the places where there is a current. So we integrate over whole space, scan the whole space, looking for any source of current. And wherever there is a current, it will contribute with r minus r prime. That's your Green's function, if you remember, or the electric potential due to point charge, the same idea. So that's your superposition principle for the magnetic vector potential. Put in the current density, and if we can do the integrals, we can, from this point on, it is pretty much algebra. So let's substitute this. Let's do this explicitly. So let's have, since the current density is given in terms of cylindrical coordinates. So we will do this integral in cylindrical coordinates. That's minus infinity to plus infinity dz prime 0 to infinity radius. So scan all the radial points and scan all the angles. That's your three integrals in dq r prime. And j is phi hat, but now I have to write phi prime hat. This is a tangent, since it's a source, prime means source. This is the tangent to all the points on the loop of wire. Times current I, then I have delta of z prime minus z naught, and delta of rho prime minus a. Notice all are primed quantities because current is evaluated at the primed position, like those are sources. And divided by r minus r prime. Now, where is r and where is r prime? So let me go a little, let me digress a little before I write that r minus r prime. So let me figure out what that is. So what is r? Observation point r will be in cylindrical coordinates. That is rho cosine phi in the I hat direction plus rho sine phi in the j hat direction plus z in the k hat direction. Right? That's your cylindrical coordinate. These are your polar x and y. That's your x, that's your y, and z. So if I were to draw this diagram, this is your loop. So r prime is somewhere here on the loop of wire. And this is your vector r, right? And that's your z-axis. And remember, this is three-dimensional, so angle phi is in the xy plane. So where is r prime? That's the second vector. That's your rho prime times cosine of phi prime I hat plus rho prime sine of phi prime j hat plus z prime k hat. What is r minus r prime? Magnitude of that will be subtract these quantities, right? So this is rho cosine phi minus rho prime cosine phi prime, and then you square it. X minus x prime square, y minus y prime square, plus z minus z prime square. So that's what I'm doing. So plus rho sine phi minus rho sine phi prime squared plus z minus z prime squared. But this is the magnitude, so I have to take the square root, right? First square it and then take the square root. That's your magnitude. Expand this out. Notice when I square this, there is a rho square cosine square phi. But when I square the first quantity in the sine term, that's also a rho square sine square phi, but cosine square phi plus sine square phi is 1. So the first term gives me simply rho square. Similarly, when I square the rho prime term, that is a rho prime squared. And there are cross terms, but the cross terms are not the same for the both. They add up, so that's minus 2 times rho prime times cosine of phi prime plus sine of phi prime. It's a big expression and it doesn't simplify. It does simplify a little using trigonometric identity. This is the double angle formula for cosine. This is cosine of phi minus phi prime. So that's equal to, let me pull that all the way this side. So that's z minus z prime square plus rho square plus rho prime square minus 2 rho prime times cosine of phi minus phi prime. That's your expression for r minus r prime. I can substitute this whole thing in the integral above. So I get this is equal to z minus z prime square plus rho prime square minus 2 rho prime times cosine of phi minus phi prime. And the whole square root, right? That's what it is. So this is r minus r prime. We just evaluated that here, and then I substituted. Should be mostly algebra. Shouldn't be bad. Any questions at this stage? Okay, if not, let me proceed ahead. If I had to proceed, I have to do the integral, and we know that the integral with respect to the argument of delta function parameter is always straightforward, trivial sort of. So I had just had to replace z prime minus z naught, and at this stage I can say I keep z naught. Earlier I was wanting to set it to 0, right? So this is, let's say this is equal to 0. Like it's in the xy plane. We won't lose much generality there with that. So I set that equal to 0. So that means I have to replace all the z primes with 0. All the rho primes with a, that means to say that the current is all in the rho equal to a value. So this becomes mu naught over 4 pi. Z integral is getting done. I have to replace rho prime with a, so this takes a value a there, and this integral is done. I still have my phi prime integral, so that's 0 to 2 pi d phi prime. I pull the I out, so I pull the I out, and whatever is left in the numerator is simply phi prime divided by z square plus rho square plus rho prime is a now, a square minus 2 rho a cosine of phi minus phi prime. And I need to do this integral. And this integral is not easy to work out. It's, in fact, this integral cannot be done. It can be written in terms of a special function. Basically, that function is defined to be this integral. So it doesn't, this integral itself cannot be done using elementary methods or using any method for that matter. So this integral takes a value of its own, and that's called an elliptic function. But we want to actually do at least some simple scenarios. Let's not worry about the exact scenario. Instead, let's say, what if this observation point was extremely far from the source? So that means to say, so this is far field approximation. That means the observation point, which is R, is very much greater than the radius of the circle A, which is also means, since remember R square is equal to rho square plus A square, right? Source point. So that also means that rho has to be very much greater than A, and Z has to be very much greater than. Okay, we want to keep both those conditions intact. So that means to say this point here. So again, if I were to draw this here, so that's your loop. That's somewhere. This is your rho, and that's your Z. You want Z. You want both of this to be large. Right, so that's our approximation. Is that any questions there? So we want.
Yeah, rho squared plus z squared.
Oh, yes. Oops, I confused it. So this is rho square plus z square. Yeah. And that requires that rho is very much larger than a, and z is very much larger. Or that's a condition we want to put in. Okay. If that's the case, then so I can replace this with r, right? So this is nothing but r. Okay, so what can I do? So this is, I'm going to take out my r temporarily. So this is equal to a of r. That's equal to, sorry, a of r. That's equal to mu naught over 4 pi. And then there is a times I. Now notice that the vector, the distance r is independent of phi prime. This is a property of the observation point. Observation point doesn't care for where my source is. So this point doesn't care for this where I am on the loop. That's with respect to the origin, it has its own point in there. So r I can pull out all the way. So let me pull that out completely. That's r, and this is 0 to 2 pi. This is d phi prime, and there is a phi prime. We will come to that. But this is now, I want to make approximations. So it's a square over r square minus 2 times rho over r times a over r. Is that clear? Hopefully that's visible there. Yeah. Okay, so how does that help me? I said in this approximation we will be able to do better. So notice that if I am having, there is an a over r is small, like a over r is small. That means this quantity is going to be significantly smaller than this quantity. Why? First of all, this is less than 1. Like this is never going to be greater than 1. Rho is always less than r. Cosine is always less than 1 because cosine function is less than 1. So whatever is the coefficient, it doesn't matter. So it is a over r that decides. If a over r is that, this will be significantly smaller than that. Or at least I can always find regions where it will be significantly small. So that's how we're looking at. So I can drop this. Right? In the far field approximation, if I'm far enough, I can always find regions where this will be significantly smaller compared to that. How does that help me? Still, I have this integral to do that. Still, it's not sufficient. But if I'm saying that this is small and I'm dropping this, why not expand this also? So that is the whole square root function there. So 1 over, let me do this here, 1 over 1 minus a small quantity x. So we're saying this is 1 minus a small quantity x. What is that equal to? That's equal to 1 plus 1 by 2x. That's a series expansion. If you want to think of it as binomial expansion, this is 1 over 1 minus x raised to minus half. So that has this expansion plus order x squared. There is some, this is not exact, there is some form with x squared, there's an x cubed. This means order x squared. I'm neglecting that. And why don't I keep that? Because I've already neglected an x squared. Who cares what it is? Because if I keep it, anyway, I have made an error in squared quantity. So this will always be small. And if I want to make this better, I just have to make this a little more smaller. So if I go in a further region, I should be able to get that. So that's your approximation. And then I can expand this out. So this is equal to then. So that's equal to mu naught over 4 pi a times I over r, 0 to 2 pi, d phi prime. There's a vector phi prime. Remember, vector phi prime is cosine phi, or sorry, minus sine phi I hat plus cosine phi prime times j hat. And this whole vector, which will have a 1 plus half of x. So this is 1.
Uh-oh. Did we lose him, or did I just get lost?
I think there's crash.
Uh-oh. What?
No cliffhanger.
Well, I guess we're getting out early today because it's not like we can email him and be like, hey, he might figure it out. I'm not sure though.
Yeah, I don't have any way to contact him right now outside of an email.
Yeah, I don't ever. I don't know. Get notes from Christian or Bodan. I think they're in class. I don't know if anybody else is.